Hello and welcome to the section 4.4 lecture video. Today we're going to talk just more about solving equations that involve logarithms or exponential expressions, and we're going to look at some new applications that we haven't talked about yet and how to deal with those. So go ahead and take out your note sheets and we can open to page 29 to get started. So here at the top of the page is simply a summary of all the different things we can use to solve exponential and logarithmic equations. So one option is to use the definition of logarithm, which is y equals log base a of x if and only if a to the y equals x. So if our variable is inside of a logarithm or inside of an exponent, we can get it out of the logarithm or out of the exponent by rewriting it using the other form, by switching from logarithmic to exponential or vice versa. Another important property is the one-to-one properties. So this says if we have a to the x of 1 equal to a to the x of 2, then those exponents have to be equal to each other. Similarly, if we have log base a of x of 1 equal to log base a of x of 2, then the numbers or the expressions inside the logarithm have to be equal to each other. The third really useful one is the addition and subtraction rules for logarithms. So log base a of m plus log base a of n. We can combine that into a single logarithm by multiplying what's inside the logs. And if we're doing subtraction, that just means we can divide inside of a single log. And last but not least, if none of these work, we can use the one-to-one property of logarithm to take the natural log or the common log of each side and use the power rule, which is so the power rule that says that the natural log of a to the x is the same thing as x natural log of a, or you can use it with log. So log of a to the x is equal to x times log of a. So this is another way to get the variable out of the exponent, is by taking the log of both sides and then using the power rule. So what we're going to do is just go through some examples and practice using these different properties and rules to help us solve exponential equations. So like in this case, all of these are ones that we have a single logarithm and we can use the definition of logarithm to solve these. So in this first case, our variable is in the base. So if we use the definition of logarithm, this becomes 5 equals x to the second power. And then we can solve that because that's just an exponential equation. So that's, we take the square root of both sides and we get plus or minus the square root of 5 equals x. And in this case, because it's the base of a logarithm, bases of logarithms can only be positive. So the answer is x equals the square root of 5. Okay, so that's the idea. Here's another one, similar idea. I can simply take the base, move it to the other side to get rid of the logarithm. So this is x squared minus 5x plus 16. Remember, the base of the common log, a log without a base written there, is 10. So this is 10 to the first. And now we can solve this quadratic equation. So subtract 10 from both sides. So we get x squared minus 5x minus plus 6. Plus 6. And then we should be able to solve this by factoring. So look at the number 6, two numbers that multiply together to get that and add to get negative 5 could be negative 1 plus negative 6 or negative 2 plus negative 3. So the first one equals negative 7, the second one equals negative 5. So that one works. So this factors is x minus 2 times x minus 3 equals 0, and then just set each one of those equal to 0. And solve. Okay, and now because we're dealing with logarithms, remember, we're available for erroneous roots, so we want to check and make sure both of these work. So if you plug in 2, you get 4 minus 10, which is negative 6. Negative 6 plus 16 is 10. Log of 10 is 1, so that works. If you plug in 3, you get 9 minus 15, which is negative 6. Negative 6 plus 16 is 10. Log of 10 is 1. So in this case, both of these work. So we get 2 solutions. So at this point, if you want, you can go ahead and pause the video and try doing these other 2 on your own. Okay. So now that you've had a chance to pause the video and try them, we can go through them together. So we're just going to use the definition of logarithm. So this first one is similar to the first one we did together. So bring the x to the other side. And then we have to solve this equation, which is one we've done before. The way you make this exponent is you want to make it into a positive 1. So raise both sides to the reciprocal. In this case, negative 2 power. So that's x equals, and then we can simplify this. This is 1 over 9 squared, right? That gets rid of the negative, and then 9 squared is 81. So this is 1 over 81. Okay, and then the second one, same idea. Take the 4, move to the other side. So we get 4 to the negative 5 halves. And you can put that in your calculator, and it'll tell you the answer, or you can do it by hand. So this would be x equals 1 over the square root of 4 to the 5th. And the square root of 4 is 2, and 2 to the 5th is 32. So this would be 1 over 32. Okay, so that's the idea. That's what we're looking for here. Okay, so that's, if you have a single logarithm, the easiest way to solve these problems is just get rid of that logarithm by using the definition. Now, if we have multiple logarithms, what we want to do is we want to do some combining, okay, to get these into a single logarithm on each side so we can use the one-to-one property. So when we go to do this, my first suggestion is to make all the logs positive. So if you wanted to, you could add the natural log of x plus 1 to both sides. And you could add the natural log of x plus 5 to both sides. Okay, so these cancel. And so I get the natural log of x plus the natural log of x plus 5 equals the natural log of x plus 3 plus the natural log of x plus 1. And the reason I did that is so now all my logarithms are positive. So that means that when I combine these, I'm going to multiply instead of divide. And division's just a little annoying. So this would be the natural log of x times x plus 5 equals the natural log of x plus 3 times x plus 1. And now we can use the one-to-one property of logarithms to get rid of the logs. And we'll do a little bit of multiplication to multiply these out. So we'll get x squared plus 5x equals x squared plus 4x plus 3. And now solve the remaining equation. So if you subtract x squared from both sides, they cancel. So we get 5x plus 4x, equals 4x plus 3. And then subtract 4x from both sides, and you get x equals 3. Okay, so that's the idea there. So if you have multiple logarithms, what you want to do is you want to combine them together to get a single logarithm. Okay. Now you can also, if you have multiple logarithms, change it so that you only have a single logarithm. If you have multiple terms that are logarithms, and multiple terms that are not logarithms, so if you have something like this, where I have 2 terms that are logarithms, but I have 1 term that is not a logarithm, I can rewrite this 5 using one of my rules. And one of the rules says that log base a of a to the x equals x. So if my x is 5, right, if this is 5, and the base of my logarithms in this problem is 2, that would mean a is 2. So if we substitute that, we can replace 5 so that we get log base 2 of x plus 2 plus log base 2 of x minus 2 equals log base 2 of 2 to the 5th. Right, so I just rewrote 5 using this rule. And so now I can combine these 2 logarithms together using multiplication. So this is log base 2 of x plus 2 times x minus 2 equals log base 2 of 2 to the 5th, which is 32. And now we can simplify, because now I can use the one-to-one property to get rid of the logarithms, and I can multiply this out. So this is x squared minus 4 equals 32, and then we just solve what's left. So add 4 to get x squared equals 36, and then use the square root property to get x equals plus or minus 6. And then you want to check both of those, but the negative one's not going to work, so this will just be x equals 6. Okay, and so that's the idea. So two basic things you want to do is if you have more than one term that's a logarithm, you'd like all your terms to be logarithms. And it's nice if your logarithms are positive. So that's a good place to start. So why don't you guys go ahead and pause the video for a second and try these other two. And when you hit play, we'll go through them together. Okay, so let's go through these together. So the first thing I would do is replace 1 with log. In this case, log of 10 to the first is equal to 1. Okay, so we can have log of 4 equals log of 10 plus log of x minus 1. And then we can combine those together using multiplication. So this is log of 4 equals log of 10 times x minus 1. And now we can use the one-to-one property to get rid of the log. So 4 equals 10x minus 10. And then we can solve. So add 10 to both sides to get 14 equals 10x and divide by 10. So 7/5 equals x. Okay, so that's how you do that one. And then the other one, we already have all the terms of the same log, but I have a negative logarithm. So the first thing I would do is add this to both sides. Okay, so that it's log base 3 of x plus log base 3 of x minus 2 equals log base 3 of 2. And now you can combine the two logs on the left. So log base 3 of x times x minus 2 equals log base 3 of 2. And now you can get rid of the log. So this is x squared minus 2x equals 2. And now solve the equation. It's quadratic. So set one side equal to 0. And now we can try and factor that, but I don't think that's going to work. So go ahead and use the quadratic formula. So x equals 2 plus or minus the square root of negative 2 squared minus 4 times negative 2 times 2 all over 2 times negative 2. 2 times 1. Sorry about that. So this is x equals 2 plus or minus the square root of 4 plus, let's see, 4 times 2 is 8, times 2 is 16, so 4 plus 16 is 20 over 2. And then the square root of 20 is 2 root 5 because we can take out a factor of 4, and now we can cancel out all the 2's to get 1 plus or minus the square root of 5. And in the end here, we only take the positive answer, right? So in the end, we get 1 plus the square root of 5 because 1 minus the square root of 5 is negative. And we can't plug a negative into a logarithm. Okay, so that's the idea on how these worked. So now what we're going to move into is I'm actually going to skip over these because these are ones with single logarithms, and we talked single exponentials. Actually, let's not skip over them. I will run through it. Let's go ahead and run through them since they're here. So these are all ones where you want to use the definition of logarithm. It's probably the best way to go about solving problems like this. So in this first, you just want to rewrite these as logarithms to get to the exponent, to get that out of the exponent. So I move the 10 to the other side, make it the base of a logarithm. So that's log of 25 equals negative 2x, and then we can divide both sides by negative 2. So it's log of 25 over negative 2 equals x. And then if you want, you can go to your calculator and plug that in to get an approximate value. So this will be log of 25, and notice how I put the base in there for me, divided by negative 2. So that's negative 0.6897, which when we round to 4 decimal places will be round up. So this would be x is approximately negative 0.6990. Let's just check that to make sure I did it right. Yep. Okay. So that's all there really is to this idea. So that's what we're looking for. Okay. So if we did the next one here, it'd be the same idea, right? So I change this into a logarithm. So move the base of the exponential to the other side. So 2x equals log base 1.04 of 2.5, and then we divide by 2. So x equals log of 1.04 of 2.5 over 2. And we can put that in the calculator just like we did the first one. So we're going to go into our algebra, click on the algebra log base b, so you can put in what log you want, which in this case is 1.04. Then inside the log, we're going to put 2.5, and then we're going to divide that by 2, and we get 11.6812. So x is approximately 11.6812. Okay, so that's the idea. So at this point, if you want to pause the video for a moment and try these other two on your own, feel free to do that. And then when you're ready, go ahead and hit play, and we'll go through them together. Okay, so like I said, this is going to work basically like the one above. So start by moving the 10 to the other side. So that's the opposite of x plus 3 equals log of 102. And then we're going to subtract 3 from both sides. So it's the opposite of x equals log of 102 minus 3. And then we're going to divide by negative 1. So x equals negative log of 102 plus 3. And then we can put that in our calculator to get an approximation. So negative log of 102 plus 3. Sorry, plus 3. So that's 0.9914. 0.9914. And then the last one, move the base to the other side. So 3x equals log base 5 of 29. Divide by 3. And you get x equals log base 5 of 29 over 3. And then we can plug that in our calculator. And we get 0.6974. Okay, and then the last type of equation we need to talk about are ones where we have two exponential expressions, one on each side. Okay. And so now what we want to do is, first of all, ask ourselves the question, can I rewrite the base, these two using the same base? And in this case, we could, because 9 equals 3 squared. So if we can, that's going to be the easiest way to do these. So if I rewrite this as 3 to the 3x minus 4 power equals 3 squared to the x. So I replace 9 with 3 squared. And so then if I use my exponent rules, 3 to the 2x, we multiply, so that's 3 to the 2x. And now they have the same base, so I can use the one-to-one property to take those out of the exponent and solve what's left. So we could subtract 2x if we want. So we get x minus 4 equals 0, and then add 4. So we get x equals 4. Okay, and so now on to the last type of problem. So the last type of problem is where you cannot write both sides using the same base. So if you can't write both sides using the same base, what you need to do is really you have a couple of options. But you need to get those exponents out. So one way you could do it is exactly the same way we did the ones on the previous page. So if I get this x plus 1 out of the exponent by moving the 2 to the other side, that's log base 2 of e to the x equals x plus 1. And now I can get the x out of the exponent by using the exponent rule. So this would be x times log base 2 of e equals x plus 1. And now we can solve the resulting equation. So I can subtract x from both sides because I need to get the x's on the same side. Nah, I'm going to choose not to use this way because I think there's a better way. I think the other way I like to do this is better. So when you have exponentials on both sides of the equation, I was going to try and do something different, but I think I'll stick with the way I normally do this, which is take the natural log of both sides. Okay, and now you can use the exponent rule to bring the exponents out in front. So this would be x, just like we were trying to do on the one side before. Okay, like that. And now you can get rid of the parentheses on the left-hand side. Okay, like that. And now what we want to do is we want to get the x's on one side. So subtract x times the natural log of 2. Now the reason I went back and did it this way is because there's a nice thing that can happen here. Those cancel. But over here, I'm subtracting two logarithms. So how do we combine two logarithms with the same base that we're subtracting? We divide. So this would be x times the natural log of e over 2. And because of that nice way to combine is why I would do it the way we just talked about, because now I can divide by the natural log of e over 2 on both sides and get x equals that, the natural log of 2 over the natural log of e over 2, and I can plug that in my calculator to get an approximation. So it's the natural log of of 2 divided by the natural log of e divided by 2. And we get 2.2589. So x is approximately 2.2589. And if you do it this way, these problems will work pretty much all of them exactly the same way. You're either going to be adding or subtracting a logarithm to each side, and so you can use your rules for combining. So if we look at the next one, we could do this exactly the same way. So take the natural log of both sides. And now we can bring the exponent out in front. So x plus 1 times the natural log of 6 equals x times the natural log of 12. And we needed, then we can distribute. So x times the natural log of 6 plus the natural log of 6 equals x times the natural log of 12. And now we need to get all the x's on the same side. So subtract x times the natural log of 6. So we get the natural log of 6 equals x times the natural log of 12 over 6, which we could simplify to the natural log of 6 equals x times the natural log of 2, and then divide both sides by the natural log of 2. So x equals the natural log of 6 over the natural log of 2, and I can plug that in my calculator really easily to get an approximation. So the natural log of 6 divided by the natural log of 2. And that's 2.5850. Okay, so that's the idea. So go ahead and flip over to the next page, pause the video for a moment, and try these two. The first one is like the first one on the last page, and the bottom two you should do like the two we just did. Okay, so now that you've had a chance to try these, let's go through them together. So in this case, the first one is very similar to start out, at least like the one we just did. So 25 is equal to 5 squared. So this would be 5x squared minus 3 equals 5 to the 2x. And so now we have two bases that are equal to each other, so we can set the exponents equal to each other. And then solve this. So subtract 2x from both sides because it's quadratic, so we want to set one side equal to 0. And then we can factor this. So two numbers that multiply to get negative 3 and add to get negative 2. Well, our only real option here is 1 and, our only real option here, is 1 and negative 3, and that adds up to negative 2, so that works. So this would be x plus 1 times x minus 3, and so we get x plus 1 equals 0, and x minus 3 equals 0. So x equals negative 1. And x equals 3. Okay, so that's the idea. But if you can't rewrite the bases using the same number, which you can't really do with 2 and 3, then you have to use what we talked about on the previous page. So take the natural log of both sides. Now use the exponent rule to bring the exponent out in front. distribute to get rid of the parentheses, subtract to get the x's on the same side, combine logarithms by using the difference rule. So we get x times the natural log of 2/3, and then divide to get x by itself. So x equals negative natural log of 3 divided by the natural log of 2/3, and now you can put that in your calculator to get an approximation. So negative natural log of 3 divided by the natural log of 2 divided by 3. So that's 2.7095 approximately. And one thing to notice here that I don't think I mentioned on the last page, but you may have noticed, is I'm using the natural log here. I like to use the natural log because it's less letters and because it doesn't look like any other logarithm you could put in your calculator, but this would work with any log. Any log you choose would work. So same idea over here. So we take the natural log of e to the x plus 1 equal to the natural log of 10 to the x. Bring the exponents out in front. Okay, distribute. Subtract the term with the x so that all the x's are on the same side. Combine by using the difference rule. And then divide to get x by itself. So the natural log of e over the natural log of 10 divided by e is equal to x. Okay, so the natural log of e divided by the natural log of 10 divided by e. So that's 0.7677 approximately. Okay, so that's the idea of how we can solve all these equations. So now you should have the tools to solve pretty much any exponential or logarithmic equation that we're going to put in front of you in this class. So what we want to do is we want to talk about some different types of applications that we haven't talked about yet. So the first one of these has to do with exponential decay, and specifically the idea of things that have half-lives. So the formula for calculating the amount of a substance, radioactive substance remaining after t years, is A equals A sub 0 times e to the RT. Notice this formula looks exactly like the formulas we've used before. So A is the end amount, A sub 0 is the amount at time 0, so the start amount, and R is the rate and T is the time. Okay? So the first problem here says, if the half-life of a radioactive substance is 10,000 years, then at what rate is it decaying? So half-life is a term you may or may not have heard before, but all it means is it's the amount of time it takes for half of a substance to decay. Okay, so in this case, if I'm using this formula, A equals A sub 0 e to the RT, they give us a time, which is 10,000. They want us to find the rate, and so the question are, what are A sub 0 and A? Well, I don't know how much I started with, so let's call that x, and I know that I end with half of that, so let's call that x over 2. Okay, so we can plug all this information into the formula and try and solve. So if we've got x over 2 equals x times e to the r times 10,000. So I could divide both sides by x. So the x's here are going to cancel. And so I'm just left with 1/2 e to the 10,000 r. And so the question is, did it matter that I didn't know how much I started with? And the answer is no. Because the x's canceled out, the amount canceled out. So what mattered was that I had half of it left. So it does not matter how much you start with. So now we can get rid of the e by moving it over here as the base of a logarithm. So the natural log of 1/2 equals 10,000 r, and then we can divide by 10,000. It's just 10,000. So r is going to equal the natural log of 1/2 over 10,000, which in this case is negative 0.000069. So that would be negative 0.0069%. Okay, so it's less than 1% a year is decaying. Okay, and this actually gives us a useful thing, which is half-life. When we talk about how long it takes things to decay, we're usually talking about thousands or even millions of years for half of something to decay away. So one thing we can do in sciences is they tend to use the half-life to really mean a rate. So if they tell you the half-life of something, what they're actually telling you is that the rate equals the natural log of 1/2 over the half-life. Okay, so that's a useful formula. So one of the ways this kind of math gets used is to date things, to date old things. So if we know how fast something that is decays away for something that is regulated in a living item, then after it dies, when it's no longer regulated, we should be able to calculate how long it's been dead for. And that's the idea behind something like carbon-14. So a piece of bone from an organism is found to contain 10% of the carbon-14 that it contained when the organism was living. If the half-life of carbon-14 is 5,730 years, then how long ago was the organism alive? Okay, so in this case, we're still using the same formula. Okay. Similar to the previous problem, we don't know how much we're starting with, but we know we have 10% of what we started with left at the end. So if the starting amount is x and the ending amount is 10, then the ending amount is 10% of that. And what we saw in the previous problem is it doesn't really matter how much we start with as long as we know what percentage of it is left. The rate is given to us in terms of half-life, so the rate is going to be the natural log of 1/2 over 5,730, and the time is what we're looking for. So if we plug all of that in here, then we can solve for t. So start by dividing both sides by x. So we get 0.1 equals e to the natural log of 1/2 over 5,730 to the t power. Then get rid of the e by moving to the other side of the base of a log. And then divide. So we get the natural log of 0.1 over the natural log of 1/2 over 5,730 equals t. And so when we write go, we can put this in the calculator. We just need to write it exactly like I wrote it there. So this would be the natural log of 0.1 divided by the natural log of 0.5 or 1/2 divided by 5,730. And we hit enter and we get 19,034.645 years. So let's call that 19,035 years. Okay, and so that's the idea. So why don't you guys go and flip over to the next page, pause the video, and try these two problems. Okay, so now that you've had a chance to try these, let's go through them together. So if the half-life of a drug is 12 hours, then at what rate is it being eliminated? Well, we can use our formula here. So the natural log of rate is going to equal the natural log of 1/2 divided by the half-life. So the natural log of 0.5 divided by 12 is negative 0.578. Or 5.78% negative. Okay, so it's being removed by the body by 5.78% per hour. Okay, so in this case, our time was an hour, so our rate is per hour. And then the second one says, if 15% of carbon-14 in a remnant of cloth has decayed, how old is the cloth? Well, we can use a little bit of information from the previous page to do this one. So in this case, we don't know how much we started with. So the ending amount then is going to be if 15% of the carbon-14 in a remnant of cloth has decayed. So that's how much is decayed. So how much is left? Well, 85%. So that would be 0.85x. The rate is the natural log of 1/2 over 5,730. That's on the previous page. Half-lives are constant, so therefore we can use the same one as we did for a previous problem about carbon-14, and then we just plug in all this information. So 0.85x equals x times e to the natural log of 1/2 over 5,730t. Divide both sides by x. We get 0.85 equals e to the natural log of 1/2 divided by 5,730t. Move the e to the other side as the base of a logarithm. So the natural log of 0.85 equals the natural log of 1/2 over 5,730t, and then divide. So t equals the natural log of 0.85 over the natural log of 1/2 over 5,730. And we can plug that in our calculator. So 1,343 years. 1,343 years old. Okay. So that's the idea. Okay, and so we could go ahead and go through. So those are examples of half-life problems. So that's using a fixed formula. But you could also do problems that involve a given formula. So this says the population of rabbits in a national forest is modeled by the formula population P equals 12,300 plus 1,000 times the natural log of t plus 1, where t is the number of years from the present. How many rabbits are now in the forest? Well, that just means t equals 0. So we just plug that in our formula. So P equals 12,300 plus the natural log of 0 plus 1. And you can just plug that in your calculator. Oh, whoops, except I forgot something from the formula. Plus 1,000. So that would have given us a very different answer. Times the natural log of 0 plus 1. Okay, so we can plug that in here if we want. So 12,300 plus 1,000 times the natural log of 0 plus 1. And we get 12,300. So P equals 12,300. And it says use the formula to determine the number of years that it will take for the rabbit population to reach 15,000. Okay. Well, in this case, we know the population, so that's going to be 15,000 equals 12,300 plus 1,000 times the natural log of t plus 1, and we just solved this equation. So subtract 12,300 from both sides. So that gives us 2,700 equals 1,000 times the natural log of t plus 1. Then divide both sides by 1,000. So that's 2.7 equals the natural log of t plus 1. And now get rid of the natural log by moving it over here. So that's e to the 2.7 equals t plus 1, and then subtract 1. So e to the 2.7 minus 1 equals the number of years it'll take for the rabbit population to reach 15,000. So we can put that in our calculator. So e to the 2.7 power plus 1 So about 15.9 years. Oh, except I added one instead of, I meant to subtract one. So it would actually be 13.9 years. Okay, and we can put that in the calculator just to show you if I fix that, that that's what we get. Yep, 13.9 years. Okay, so that's the idea. So there's a problem that the formula has a logarithm in it, and we're solving the equation. So go ahead and look at this last page of our notes, pause the video here, and see if you can try this problem. Okay, so let's go ahead and go through this together now that you've gotten a chance to try it. So biologists use the species area curve n equals k log of a to estimate the number of species n that live in a region of area A where k is constant. If 2,500 species live in a rainforest of 400 square kilometers, how many species will be left when half of this rainforest is destroyed by logging? Okay, so the first thing we have to do here is we need to figure out what k is. So they give us an example of the number of species equals k times the log of the area. Okay, so k is going to equal 2,500 over log of 400. Okay, and so now we can use that information along with the fact that we want to know half the rainforest is destroyed. Well, if half of the rainforest is destroyed, then we only have 200 square kilometers left. So we can do n equals our k, 2,500 over log of 400 times log of 200. So that'll be 2,500 divided by log of 400 times log of 200. And so we get 2210.8, so 2211. So n equals 2,211 species. And it says a rainforest, B says a rainforest of 12,000 kilometers supported 3,500 species in 1950. Due to intensive logging, what remains of the forest this forest supported only 1,000 species in 2000. What percent of the rainforest has been destroyed? So this one's a little trickier, but we start off the same way. We first have to find k. So we know that the rainforest had 3,500 species when the area of the rainforest was 1,200 kilometers. So log of 1,200. So in this case, our k is going to be 3,500 over log of 1,200 equals k. And so in this case, we know how many species it had in 2000, so that's 1,000 equals our k, 3,500 over log of 1,200 log of a. So we need to find a. So first, divide both sides by 3,500 over log of 1,200. So these cancel. And so when you do that, what you actually get is you multiply by the reciprocal. So this would be 1,000 over 3,500 times log of 1,200 equals log of a. And then we need to get rid of the log so we can raise this thing to the 10th power. And we can simplify this a little. 1,000 divided by, well, let's go ahead and just use the calculator to make it easier. So 1,000 divided by 3,500 is, I believe, 2/7. Yeah, so 2/7. So this will be 10 to the 2/7 times log of 1,200. Will give us the new area of this rainforest. So 10 to the, whoops, 10 to the 2 divided by 7 times the log of 1200. So let's just make sure we did that right. Yeah, that looks right. So I'm getting 7.58 square kilometers is all that's left. And so they asked for the percentage. So to do that, you just take 7.58 divided by 1200 times 100. And then I'll change it into a percent. And so you get 0.631 or 0.632 is what's left. So 0.632 is how much of the rainforest is left percent. So that means 99.368% has been destroyed of this rainforest. Okay, so there's some examples of how logarithms can be used and how exponentials can be used. So that's it for section 4.4. Don't forget to do your homework and the quizzes. And if you have any questions, feel free to call, email, or text.